Welcome to NPTEL lecture on array antenna. Actually, we were seeing wire antenna, some of the wire antennas like dipoles, monopole, folded dipole, etc. we have seen. The logical next step would be to see an antenna which by area radiates power, that means an aperture type of antenna. But before that, in this wire antenna discussion, we want to point out one thing. If we look at the wire antennas that we have seen till now, the pattern, wire antenna pattern looks like this. You see that in the E field or in the theta direction, we have a directed beam, but in the phi direction or in the azimuthal plane, we have a non-directional pattern. Now, that has some problem or actually the wire antennas that we have seen, all wire antennas are symmetrical. Now, symmetrical from the feet point of view, and for that this is natural that in the azimuthal direction there will be no directional nature in the radiation pattern. Now, that is very good for broadcast type of antennas, because these wire antennas are heavily used for radio broadcast or TV broadcast sort of applications. But the moment point to point communication proliferated with the help of this cellular telephony, etc., another problem came that if I have in the azimuthal direction, that means I have an antenna compared to the antenna axis in a perpendicular plane, I have an uniform pattern. Then if there is another source of radiation or another transmitter nearby, then there will be lot of interference coming. So, unless and until I can shape this, there will be problems, because there will be strong interference. Like the problem I was saying, that suppose Calcutta radio station is radiating and nearby there is Dhaka radio station. Now, if Calcutta radio station does not put a null in the direction of Dhaka radio station, then Dhaka radio station's interference will be there. So, you can see to the next slide, this is the problem, that suppose I have one of the, this is one transmitter. If there is another transmitter, then it is required that in that direction I should have a null, but that is not possible with a wire antenna that we have seen till now, because of their this azimuthal pattern being, that is why we have seen that the radiation pattern does not have a theta dependence, radiation pattern is fully radiation pattern does not have a phi dependence for the antennas that we have seen. Now, only to rectify this, you see, if instead of a single antenna we use two antennas or more and more number of antennas, then this problem can be rectified. That is why you will see that basically these communication antennas, they are sealed in a box. If you look at the this cellular telephony base station antennas, you will see that they have a long box. Actually, if you open the box, actually that box is nothing, it is a sealed thing. If you open the box, there will be antennas, they use something like patch antennas, but there are an array of patch antennas. Instead of patch antenna, they could have used dipoles also. So, in some of the stations you will see number of dipoles together. So, that array antenna is to shape the pattern, so that the interference, etc., can be avoided. Now, let us look at this. First, what we will do, we will now take what happens if two array antennas we place together. That means, let us say that the antennas are still in the z directed things. Suppose this is one dipole, this is another dipole, or this is one monopole, this is another monopole, etc. And so they are along the x axis, the antenna's current is in the z directed, and they are separated by a distance d, and we are observing what is happening in the azimuthal plane, that means in this p direction, some arbitrary point p. So, the center of these two antennas thing, actually here now the antenna axis will be, or the array axis will be called the x axis. Antenna is z directed, but antennas are oriented along x axis. So, the x axis is the array axis, the center of that point, that is the center of the coordinate also. So, the field point is p. So, center of this array axis, that the radius vector of point p is r. So, this antenna, if I from this antenna is at a distance of r1 from point p, this second antenna I2, that is at a distance of r2 from the field vector p, and if we project this p in the xy plane, then that projection has an angle phi, that means this p is at an angle phi and also from here theta. So, this p is at a distance r theta phi. Okay. So, now we are interested that what happens to this azimuth or to the whole field pattern if we at the point p. So, we will first evaluate the field at point p. This is the same viewpoint. Obviously, we are interested that p is at the far field. So, you see in this structure we have now just took a snapshot that at the axis antenna 2, though it is an wire antenna, we have made it a point just for the drawing sake. Antenna 1, antenna 2, antenna 1 is at a distance d by 2 from the center, antenna 2 is at a distance d by 2 from the center. So, that the inter antenna or inter element spacing is d. This is point p. Now, p is at far field. So, r1, r2 all are much larger than d. So, that is why they are all parallel rays, and r1, r2. So, they are actually in the in the amplitude part we can say that r1, r2 are similar, but in the phase part we cannot do. So, we will have to later evaluate what is r2 and what is r1 with respect to r. So, as seen from this you can easily see that basically I can write r1 is nothing but r minus d by 2 cos phi, and r2 is r plus d by 2 cos phi, okay, for the phase part. So, that will do. So, now let us start finding what is the field. So, we know if it is a any wire antenna, let us so individual element, suppose this antenna 1 or antenna element 1, antenna element 1, we have already seen that its field, far field can be, far field is E theta directed. So, I can write that the far field A for antenna 1, that can be written, can I say, if you look at your actual expression, that already we have found out these expressions earlier. So, from there you can see that actually I am writing here the E theta for a far field is something like j 60 I m e to the power minus j beta naught r by r f theta. This was the expression that we evaluated. I do not know whether we have seen it or actually we have seen this one. I think that this one we have seen. This becomes this if we put the value of this eta naught as 125. Okay, so based on this, I think I can say this was for the dipole. So based on this, I think I can write that E theta 1, the field at point P, E theta 1 at point P due to the antenna 1, that can be written as some constant I so this k, actually everything here you see j, eta naught, this 2 pi and f theta, everything I have put here. That means k is actually then it is a constant and it is a function of theta. So, all theta dependence also I have included here, because I am not interested to say what is the theta dependence of the resultant field. I am interested to see what is the phi dependence of the field. So, k has absorbed all the coefficients, and what is I? I is the current fed to this antenna. So, if we see at this antenna 1, that has been fed with a current I 1 and its phase is, with respect to some reference, its phase is alpha. So, this excitation of this is a thing. Actually, in array antenna, this complex excitation, that means antenna current excitation, that is in our hand. So, here we are exciting I 1 with a current I and angle alpha, whereas I 2 is excited with the same current. We could have given different current, but let us say to start with simple thing, same current amplitude I, but angle is 0. With respect to I 2, I 1 current leads by an angle alpha. So, this current I alpha and the distance is R 1. So, this is the far field due to the first antenna element. The second antenna element can be written as I 0 R 2 e to the power minus j beta naught R 2. Actually, this is true for any wire antenna. Instead of dipole also we could have taken. So, this thing, only sometimes the terminal currents of the non-resonant type of dipole, they here these are the terminal currents or this maximum currents which occurs at the feed point. In their case, the maximum may not occur at the feed point. So, that by some constant relation they can be extrapolated. Okay. Now, so how this excitation is done? You see that both are excited with the same current amplitude, but with a different phase. That means, this, look at here, this I 1 and I 2 we can feed with the same source, but between I 1 and I 2 in the path there should be a phase shifting network. So, that this current is shifted by a angle alpha, that is the only trick. So, there should be a feeding network in the line feeding one of the things. Now, other things are okay. You see the far field we have seen that is dependent, varies as 1 by r, 1 by the distance from of the observation point from the source, and also it has a phase, space phase e to the power minus j beta naught r 1. Okay. So, now what will be the total field at point P? So, it will be theta 1 plus E theta 2 P, and that we can say that again R 1 and R 2 we say we are at the far field. So, far field means that I can say R1 is same as R2, same as let us say R for in the denominator or amplitude part, not here. So, I can write K, then I, then R, and here I can write e to the power minus j beta naught R1, and also I will have e to the power j alpha because of the current excitation, and here I have e to the power minus j beta naught R2. Okay. So, this thing now I will have to put these conditions that in the far field R1 will be R minus d by 2 cos phi, and R2 is R plus d by 2 cos phi. So, putting this, I can write that E theta will be K I R e to the power j alpha by 2 e to the power minus j beta naught R e to the power j beta naught d by 2 cos phi plus alpha by 2 plus e to the power minus j beta naught d by 2 cos phi plus so this can be so this for my convenience I can write as 2 e to the power j alpha by 2 k I So, you see that this one I have written that this whole part, I am writing as an array factor. Previously you see in the dipole expression we have f theta, actually this f should be small f. So, that this is from an element pattern. So, this is the theta variation. Here you see this thing is a function of only d and alpha. So, both are arrays parameter, that d is the separation between the two antenna elements and alpha is the progressive phase shift of the current of one of the antenna. So, apart from that all are constant terms. So, this is called array factor, capital F theta phi. So, this is varying as 3 phi. In general, it can vary also with theta, that is why we are writing theta phi. What is this? You see, this is nothing but, can you recognize this? This was nothing but our element pattern. This is the pattern of the array, and one element, you see its far field. So, that means now total field, you see this is a constant part, and if I take the magnitude of this, then can I write that this is the element pattern? Obviously, this is a field pattern because this is E theta, and this is the array pattern. So, by arrays geometry I am getting this pattern, from the element I am getting this pattern. So, what is E theta? E theta or the total this array antennas pattern is nothing but multiplication of the element pattern with the array pattern. This is a general result, this is called principles of pattern multiplication. So, the resultant field is the product of the pattern of the individual identical elements and the array factor. So, this is principal pattern multiplication. For two elements we are seeing this, just later maybe in this lecture or in the next lecture we will prove it generally, that for any type of array, this is a general thing that element pattern and array patterns gets multiplied. Now, what was our interest? Our interest centers on the magnitude of E theta as a function of phi, because we motivated to have a array of two elements from there. So, let us see that. So, let me again rewrite the argument of the array factor, that means this angle psi, that was, what was angle psi here, psi, so I can write half beta naught d cos phi plus alpha. So, by putting beta naught value I can write pi d by lambda naught cos phi plus alpha by 2. So, you see what is this psi? This variable psi is nothing but it is a function of the electrical separation distance of two antennas. D by lambda naught is the electrical separation distance, and also it is a function of alpha, which I already explained as the progressive phase shift. So, now I can easily write what is the magnitude of the total field E theta, that is, it can be written something like m by r cos phi. What is m? This m is 2 k I, okay, some constant already seen with this. These are dependent on, one is the excitation, another is what type of element I am using. So, what will be the shape of the power pattern? Obviously, the shape of the, because radiation pattern is basically power pattern. So, in the far field we know the H phi, the magnetic field, that will be some constant into this, that means eta naught into this. So, that means square of this pattern will be the power pattern. So, this one you see this cos, depending on cos phi. So, various values you will see this pattern will have various maxima and minima in this pattern. So, the pattern will be symmetrical about a line joining the antennas, because in the x axis we have taken the two antenna elements symmetrical. So, that means what is the adjustment we have? The adjustment we have is that I can play with the inter element spacing. So, two elements, what is the spacing that if I adjust, I am changing basically this psi, and from that this cos psi value is changing. So, the pattern will change. Also I can adjust this value of progressive phase shift alpha, and by that I can change the pattern. Suppose the antenna spacing I take as, for an example, that let me take d is equal to lambda naught by 2, half wavelength long, half wavelength distance separation, and let us take that alpha is 0, no phase difference, both the things are fade in phase. So, obviously physically we can say that if there is no phase difference, then at point P there will be the maximum of the thing, because R1 and R2 are symmetrical. If we again look at this, so if I have no phase difference, that means alpha is 0. So, it will peak at this point, because this pattern also peaks at a point here, this one peaks at a point here. So, here there will be peak. Let us see that for this case what is becomes the value of phi. Phi becomes, you see, pi by 2 cos phi. So, now the pattern will be, or the array factor becomes cos psi, means cos pi by 2 cos phi. So, for a fixed distance r, this cos phi or this pattern will have null at point when pi by 2 cos phi becomes pi by 2. So, when that can becomes, so that means for values phi is equal to 0 degree and 180 degree, there are nulls. So, you can see that this is the pattern. This first one, you see we have taken d is equal to lambda naught by 2 and alpha is equal to 0. So, you see that this is the array axis. So, this is 0 degree, that means here there is a null, this is 0 degree, this is 180 degree, because this angle 180 degree. So, here also I have a null in the pattern. Now, where is the maximum? So, maximum, you know that we can find out the maxima by differentiating this pattern with that cos d phi of cos pi by 2 cos phi, you can do. Now, this can be minima maxima, that you can check whether it is minima. So, or in general if we do that because this is a special case, I will come here, but in general let us do d phi cos pi d by lambda naught cos phi plus alpha by 2 is equal to 0. So, this if you do, it becomes sin phi sin pi d by lambda naught cos phi plus alpha by 2 is equal to 0. So, the one of the solution is sin phi is 0. So, that means the phi is equal to 0 gives you either a maxima or minima. Similarly, phi is equal to 180 degree also max or minima, and this other condition gives you that pi d by lambda naught cos phi plus alpha by 2. This will also give maxima or minima at 0 plus minus pi plus minus 2 pi. So, you can put the value of our thing, and suppose if we put d is equal to, in that particular case, d is equal to lambda naught by 2 and alpha is equal to 0. So, you can put pi by 2 cos phi is equal to 0, gives you that the phi is equal to pi by 2, and if you check, this will be a maxima which happens here. You see pi by 2 is this, maximum is at pi by 2. This is pi by 2, this is, you can say, minus pi by 2 or 3 pi by 2. So, there are maximum. So, this. Now, you see that if you go on this, suppose I take lambda naught by 2 and alpha is equal to pi, that means progressive phase shift pi. You see, instead of the pattern peaking in the perpendicular direction to the array, it peaks along the array axis. Actually, this will prove later. This type of array, the first type, is called broadside array, where the maximum takes place perpendicular to the array axis. This is an example of an end fire array, where the maximum takes place at the along the axis. Okay? Just by changing the progressive phase shift, instead of no phase shift, we have given a 180 degree phase shift between the two elements, and that gives is end fire. Similarly, you can take progressive phase shift pi by 2, distance pi by 4. Here you see the pattern is here. So, there is a null. Suppose if there is an interference from this direction, you can put a null here, other direction almost circular type of thing. So, this also helps to do, and actually you will see that by using this and principle of pattern multiplication, you can split the beams. So, when we say that nowadays MIMO antennas, etc., or an antenna array has 4 beams, 5 beams, all these are you can do from here. Okay. So, we won't pursue more, because pattern multiplication is general, but actually if we derive the general principles of array antenna, we can get much better views. So, let me see, this is illustration of pattern multiplication. You see, from that, if I have 4 such beams, suppose this is lambda naught by 4 and these are the 2 antennas, if their separation is lambda naught by 2, this is an end fire type of a. So, now if we take 1, 2, 3, 4 antenna elements, and so this one and this one, they are separated by lambda by 4, this one and this one lambda by 4, this is lambda by 4. So, you see there are 2 groups here, one is this 1, 2 and 3, 4. If I do like this, so 1, 2 will give me a pattern like this, but this pattern will come here. Similarly, 3, 4 will come this pattern here, and then that group has an inter element spacing of this lambda naught by 2. So, there will be a, due to that array, that subgroup array, you can have this. So, this pattern will be multiplied by this and another one here. So, that will result in this type of pattern. There will be 3 such beams. Okay. So, this, but this is you can take the help of pattern multiplication, but more important, this you can generally derive also if we have this way thing. So, next we will start with n element array. So, suppose I have these n number of radiators, all identical radiators, but at different distances from the coordinate system they are available, and I am looking at the far field. So, here there is let us say that this ith radiator is along this here ith radiator is along this direction, and so the field point is here P. So, this AR vector is the unit vector along the field point. So, any ith radiator that will have a difference from this AR vector, that means this is a path, but suppose I am having this ith radiator. So, ith radiator will have a difference of AR dot Ri, because that will be the AR is this, Ri is this vector. So, this part, that means cos of this AR Ri cos of this angle, that will be the path difference between the two. Okay. So, with that, so suppose if I have R3, then it will be AR dot R3, AR dot R1, etc. So, I can also tell you, because the figure is not so good. This is taken from Collins' book. So, I can say this, the same figure, what I mean is this is the coordinate origin, let us say this is the point P. So, along point P I have an AR vector, unit vector along this direction, and let us say that I have a radiator here. Here is an current element, let me call it Ri. So, this will have a path length like this, this will have a, so this path at this point, how much is the difference between this path length and this path length? Can I say that this is nothing but this difference, and that difference is, what is the value of this difference? This is nothing but AR dot Ri. That is what I was saying. So, that means when we will write what is the path for Ri, we will write it is R minus AR dot Ri. This is the Ri is equal to R minus AR dot Ri. This much I was trying to prove. Actually, here the figure did not come nicely, that is why. But otherwise, if I look at here, so all these are elementary antennas. I have n such elementary antenna. To start with, I am distributed them haphazardly, but each I know their coordinates, etc. So, I can find at the far field, the total field will be superposition of all of them. And also there is, you know, that apart from this geometry, there is another important thing, that every antenna element is getting excited. So, let us call that the excitation, actually this excitation is a complex excitation, I will call it Ci. So, or I will call it the amplitude Ci and phase alpha I. So, that means each excitation or current for each radiator, I am not exactly writing current, because this concept is general, this is true for wire antennas or aperture antennas, etc. In case of aperture antenna, we will see we do not have conduction current, there we will have some other type of thing. Maybe those of you who know it, we generally like to call it magnetic current, etc. So, that is why I am writing this excitation amplitude is Ci and the phase of that with respect to any reference is alpha I, and the central element or the central point, that is there we are placing a reference antenna, and that reference antenna radiates with C I 1 and alpha I 0. So, with respect to that one, that excitation, these are C I alpha I is the excitation. The radius, I have already said, the radius vector of the observation point is r, and obviously theta phi is there. So, its radius vector is r and its unit vector I have shown here. So, now let us write the reference antennas field. So, reference antenna at the center of the system. So, that is radiating a far field E r, that I can write as f theta phi e to the power minus j k naught r by 4 pi r. So, what is a theta? Radiation pattern of elemental antennas. Elemental antennas means they may be dipole, they may be rectangular waveguide, they may be horn, whatever, but elemental means element of this array, and we assume that all are having same type of thing, that is called this. Here the in an array generally the elements they are same, though very sophisticated arrays there may be difference, but here we will not treat that, all are having the radiation pattern as phi theta. And in the far field we know that r will be much greater than r I magnitude. The rays from all the radiators are essentially parallel, and I have already written that r I is the distance, that I can write as r I r minus a r dot r I. So, the far field produced by the ith antenna will suffer a propagation phase delay by an amount k naught into this smaller than that of the reference antenna. So, now I can write the resultant field. So, this was for a single element. So, E r for all will be I is equal to 1 to n C I e to the power j alpha I f theta phi e to the power minus j k naught r plus j k naught a r dot r I. I can take out f theta phi e to the power minus j k naught r, and I dependent terms are inside, C I e to the power j alpha I plus j k naught a r dot r I. Okay. So, with this lecture is concluded. Now, in the later lecture we will see that what is the implication of this part. Thank you.